Standardization is the cornerstone of efficiency and interoperability. In Ethereum ecosystem, we create standards called as EIPs. Ethereum Improvement Proposal, aka EIPs, facilitate clients' coordination by providing a common reference point for discussing and implementing changes. Welcome back to PEEPanEIP, where we learn about an Ethereum improvement proposal with the author to follow the motivation, specs, and utility in the ecosystem. This is episode 123, and I'm your host, Pooja Ranjan. Today, we will talk about EIP-4881 Deposit Contract Snapshot Interface. Originally documented in January 2021, this EIP aims to establishing the format and endpoint for transmitting a snapshot of the deposit Merkle tree. The proposal has recently been moved to final status, meaning it is available as a standard for clients and community. To provide an overview of the proposal, we are joined by the author, Mark McKee, also known as EthDreamer. Welcome to PEEPanEIP, Mark. Mark is a core dev at Lighthouse. As he mentioned, Lighthouse is a consensus client for the Ethereum blockchain. We had the opportunity to talk about the client with him during the merge upgrade. If you missed the talk, follow episode 81 to learn more about Lighthouse. It's lovely to have you back, Mark. It's been a year since we had you last. May we kick off today's talk with a brief introduction and your journey with the Ethereum for our new listeners.
Yeah. So my name is Mark. I have a little introduction about me on the first slide. So yeah, for those who don't know, I'm a Lighthouse developer. That's primarily what I do. I've been working on Lighthouse since April of 2021, and I designed EIP-4881 mostly in 2022. And I'll get into a little bit more about that later on. And yeah, I go by EthDreamer on most forms of social media, not just Discord and Reddit and Twitter and GitHub and so on. So if you want to reach out to me, that's how you find me.
Thanks for the introduction. Without further ado, let's peep in.
Yeah, so before we can kind of get into the CIP, I got to give a bit of background on the Ethereum deposit process. And so if you've ever wanted to become a validator, the first thing you're going to need to do is to make a deposit to the deposit contract. And that will cause the contract to emit what's called a deposit log. And the important thing here is that those logs are stored on the execution nodes. And in the original design of Ethereum, we didn't always have them merged. So the execution chain and the consensus chain were not as one; they were separate chains. And so we came up with this method of having self-contained proofs of deposits, so that the consensus node didn't have to have like a lockstep connection with an execution node. And this is all kind of a remnant of the pre-merge days. So I'm just kind of describing the deposit process as it exists today and as it was designed for those pre-merge days. So if you've ever made a deposit, you'll notice, or you will have noticed, that the beacon chain doesn't recognize it right away. So let's say the head of the chain is here and you've made your deposit at the top of the chain in the most recent block. The beacon chain is actually not looking at the most recent. It's looking a ways back at this red interval that I've colored here. And so it's really only adding or considering new deposits within this interval. This distance between the head and that interval is controlled primarily by the ETH1 follow distance. That was a parameter, again, a remnant of the proof of work and proof of stake split. The idea was twofold in making this distance quite long. One was just that there's plenty of reorgs in proof of work, more than in proof of stake, and we didn't want a deposit to be reorged out of the chain or be double spent, so it had to be sufficiently deep in the chain that we knew it wasn't going to be reorged out. And two, in case there was any kind of issue on the proof of work chain, like some long-lasting fork or something, we wanted to give us enough time as consensus devs to maybe make a fork or do something so that it wouldn't end up, before it ended up reaching the beacon chain and messing with the proof of stake chain. So we made this about 8 hours. So it's kind of a long time. But yeah, so you'll have to wait until the chain, once you've submitted your deposit, you have to wait till the chain gets a bit longer, and then your deposit ends up within that interval, as it kind of shown. And at that point, the beacon chain will start adding deposits from that interval. But before it can do that, they have to, all the validators have to come to consensus on the head of the deposit contract at the head of the interval, at the top of the interval. And specifically what they're coming to consensus on is this ETH1 data object, which contains the deposit root, which we'll talk a little bit more about in a moment, how many deposits are in the tree, and the block hash at the end of the interval. So they're coming to consensus on this object at the end of the interval. And once they've come to consensus, they'll start adding deposits. So the way that works is like for every new block, you'll just take some of the deposits out of this interval, stick them in a block along with their proofs. Again, we'll talk a little bit more about that. And then you'll add that block to the chain and the deposit will be included on the beacon chain. And then the next block will come along, grab a couple more, and this will just kind of continue on until all the deposits are included up to the cutoff. And that's usually what happens. And then the interval will just move forward like that. So yeah, that's kind of the regular deposit process. A little bit of fun background on the deposit contract itself. It was deployed on October 14th, 2020. I don't think it was announced until about a month later. It was one of those always has been memes. This is the canonical address for the deposit contract. I basically put that in as many places as possible. So here's another place. The account that actually deployed the contract was funded with Tornado Cash. So presumably we don't know who actually deployed the deposit contract. Could have been anyone because the contract was open source at the time that it was deployed. Deployment cost about 0.31 ETH, and the remaining ETH was sent to the WikiLeaks donation address. So it's the only one address from, or one transaction deploying a contract from a serious account, and then they never transacted again. So the whole point of the deposit contract is to implement this progressive Merkle tree design, which is quite a novel design that was suggested by Vitalik in 2019. And it's cool because it maintains just a couple of hashes. So the number is actually 32, but it can store up to 2 to the 32 deposits. So it's very efficient in its storage, which is great for gas usage. So yeah, we have to explain a little bit about this Merkle tree because it's kind of a special Merkle tree. It starts out with all zeros at the bottom, like when there's no deposits. So like the tree is completely empty, every leaf is all zeros. The way any Merkle tree works is that the value of a node is the hash of the nodes to the left and right. So like I said, the bottom is all zeros at the start. So if we're just looking at the leftmost 2 leaves, if you hash two Z0s together, you'll get Z1. These are called zero hashes. And then you hash 2 Z1s together, you get Z2, and so on. 2 Z2s, you get Z3, 2 Z3s, you get Z4, and you go up. And that's just the regular way that a Merkle tree works. Now, when there's a deposit in the tree, someone will say make the first deposit like this. That'll change the hash above, which will change the hash above, and it just propagates upwards. And the tree will just kind of continue evolving from left to right like this. And that's important. Basically, the tree will just do this as it fills up with deposits. And note that the deposits are stored at the bottommost leaves, and the upper nodes are determined by the hashes of those deposits. So yeah, this is kind of the special property of the tree. To kind of give some background into what a Merkle tree does, it's data structure used to efficiently and securely verify the integrity or authenticity of some set of data. So in this case, the data that we're verifying, that the consensus layer is verifying and proving, is new deposits to the deposit contract. Remember I said that all the nodes come to consensus on this deposit root, or this ETH1 data object, which has a deposit root. Well, that root is the red node at the top of the tree there. So they've all come to consensus on this single root, which is a 32-byte value, which is nice because they don't have to come to consensus on a lot of data. They can come to consensus on one hash. And that basically means they've come to consensus on the state of the entire tree up to some certain point. So in any Merkle tree, if you want to prove that something is in the tree, so in this case, we're proving a deposit is in the tree, say this purple one that I've singled out, you'll need its sibling. So that's the first sibling. You can hash those two together to get the parent. You'll need the parent sibling, which you can hash together to get the parent again. You'll need that sibling, hash together to get the parent again, and so on. The nice thing about this is you'll notice that if I want to prove the purple deposit, I only needed 4 hashes. And all I have to do is check this equation that when I hash them together, it equals the root. And I've proven that that deposit is in the tree. This is how all Merkle trees work. And the nice property formally specified is that the size of the proof is logarithmic in the number of elements in the tree. So it's quite efficient to prove that a deposit has been included in the tree. So now that we've kind of given background, we can get into the motivation of 4881. So every consensus client has to maintain a copy of this tree in order to prove new deposits. And without 4881, the only way to do that is to reconstruct the deposit tree by replaying all deposits since the launch of the deposit contract. So you're going to have to, the consensus client's going to have to ask the execution node, like, give me all the logs from the launch of the contract all the way up to today, and so that I can rebuild this tree. Today that takes about 15 minutes, but like new deposits are being added all the time. And so this is taking longer and longer. And where the motivation for this really came from is, like, I know a lot of people have kind of seen this photo of Amphora, but at that time, and we were actually in that room, we were discussing like making changes to the execution layer to kind of prune old data. That discussion eventually turned into EIP-4444, if you're familiar. But we specifically mentioned that the deposit contract, that the deposit, that we couldn't prune old logs because we would lose the deposit logs and we wouldn't be able to rebuild this tree. And so that's what kind of got me thinking about this. So this particular, the deposit Merkle tree has a very nice property, which is that it fills left to right. Not all Merkle trees do this, but the deposit tree does. I mean, I guess in principle it could have filled right to left, but like most Merkle trees, you can alter any node in any order, and that's not the case for the deposit tree. It has a progression to it, and Ethereum has the property that it finalizes under proof of stake. And so once a deposit has been included on chain, there comes a point where we know that that deposit will never be reverted, and we'll never need to prove that deposit again. So basically, the left side of the tree contains information that will never be needed again once it's been finalized. And so that was the key, that was kind of the key insight here. And so that actually allows you to drop a lot of the old hashes that you'll never need again. And so like here, say like the left 5 most have been finalized. So we've replaced these 5 these what would be 6 hashes down to just 2 hashes, F0 and F1, because we'll never need to prove these again. And so we can just drop all the old hashes and yeah, it ends up, that's kind of the efficiency gain. The nice thing is, like, say the tree evolves further, if the finalized tree ever contains a power of 2 number of deposits, then the entire tree will actually collapse to just 1 hash, the entire finalized tree. Yeah, the tree basically kind of moves like this, where we can just drop any old deposits that have been finalized and go as high up in the tree as possible on hashes that we know will never change. And we have this nice property that once n deposits have been finalized, we have to keep at most log base 2 of n hashes, sometimes less, depending on how close the number of deposits is to a power of 2. And so you can kind of package up the finalized deposit tree into like a small object, which I call the deposit tree snapshot. And then furthermore, you can transmit that snapshot when consensus nodes are weak subjectivity syncing. So for those who don't know, weak subjectivity sync is this nice thing where consensus nodes don't need to sync the chain all the way from Genesis. They can, if they know another node that's like already synced on the network and they trust it, they can just ask it like, hey, what's a state, generally a finalized state that's not going to be reverted, that's kind of near the head. And you can start from the middle of the chain, kind of near the head, and just sync right up to the tip of the chain, and you're like ready to go like that. You don't have to replay all the blocks from Genesis. You can start right before the head and sync up, and it's significantly faster. And then you can just backfill all the blocks going backwards, which is much, much faster than going forwards. So yeah, like I said, you can kind of take those hashes, those F0, F1, F2, and stick them in this little array, finalized array here in the snapshot. And then those other fields are just the same fields that are in the ETH1 data object, plus the block height for convenience. But it's very small. This is the actual snapshot of the deposit tree last night. You can see there's over 1 million deposits for the deposit count right now. Looks like 1,031,000, and it's only 13 hashes. So like this small object encodes over 1 million deposits in the deposit contract. It's very cheap and fast to transmit. So now when a consensus node is weak subjectivity syncing, if you're using these snapshots, you don't have to download all the deposits since the beginning. You can just grab this snapshot and download deposits since the finalized tree, which in practice isn't more than, a couple of hours ago. This process in practice takes about 8 seconds instead of 15 minutes. So it's significantly faster. This design also allows consensus clients to just continuously drop those old hashes, which saves memory and disk. And now that we don't have to have the old hashes to sync the tree, the execution clients could safely prune those old logs and they wouldn't have any issues. So that's basically the effects we were going for when designing this. During the design, I did spend like a great deal of time creating a nice Python spec to hopefully make it easier for other teams to implement, which worked out pretty well, actually. I did collaborate a little bit with Proto Lambda at the beginning, and also Zahari. Funny enough, Zahari had already implemented this before I had even started work on it, but I didn't look at what he did. I kind of came up with my own design, but nevertheless, they ended up being very similar, or at least a very similar idea. I'm not exactly sure that he designed it in exactly the same way, but we converged on very close to the same thing for the deposit snapshot. And then we just kind of collaborated to ensure we'd have the same format, so they're cross-compatible. But I guess that's a good sign because it speaks to the soundness of the design if two engineers came up with a very similar design. So yeah, it's finalized now. It was implemented in Nimbus very early on. Lighthouse has supported it since version 3.3.0, which is it's back in 2022. So like, if you're running Lighthouse now, you definitely have it because that was before the last fork. So you have to be running a version which has it. Teku added support. They didn't even talk to me, which I guess is another good sign that it was just easy for them to implement. Prism added support as well. And then we got Checkpoint Z to add support, which is the one that really counts. If you've ever used weak subjectivity sync, you might have seen this kind of page, this Checkpoint Z. This is the screenshot of like the ETH Staker version. But this is kind of the site you'll go to if you want to sync a consensus node very quickly. And this natively supports the snapshot. So if you're running any of those, Lighthouse, Prism, Teku, or Nimbus, and you connect to Checkpoint Z or any other Lighthouse, Nimbus, Teku, Prism node to weak sync off of, you should get the snapshot. Yeah, so in terms of future directions, we've had the merge now, and so we don't need a lot of this old machinery that was designed to work around the fact that we were not merged when the beacon chain started. So a lot of this work is in EIP-4881, where you'll just have like in protocol deposits. The nodes no longer need to vote on the state of the chain at some point because the consensus nodes already know the state of the chain because the execution block is embedded in them. So it doesn't really make sense to have to vote on what information you already know is there. And so consequently, these Merkle proofs are no longer necessary. And consequently, this will eliminate the need to distribute and maintain these snapshots. So yeah, I mean, a lot of this work could be obsoleted. However, if there's another situation where you have a Merkle tree that moves from like one direction to another and kind of fills out and doesn't change, and you're doing this on Ethereum that has finalization, you could have another application of this deposit snapshot or just Merkle tree snapshot scenario. Not sure if that'll be used or not, but yeah, we'll see, I guess. So yeah, it's a pretty short presentation. It's a simple EIP, but thanks for having me.
Wonderful, thank you. I mean, standardizing the data structure used to transmit the depository and standardize the beacon API endpoint to fetch the depository was definitely a good motivation to document this proposal. The presentation was good. Yeah. As you said, it was short but interesting. It was really nice to follow the background of the proposal and the beacon chain deposit process. And of course, the photo that you shared about the amphora, that's quite popular
Yeah, it was funny. I mean, we briefly mentioned it at that time, and someone mentioned that Nimbus had done it. And so I kind of knew it was possible, but it wasn't really spec'd out at the time. And so, yeah, I figured we were moving in that direction. So I just kind of took the opportunity. And then once I had implemented it in Lighthouse, I didn't know really like where the specification would live. At that time, I didn't realize, I know this is changing now, but it's actually kind of rare to have a consensus client change be put in an EIP. EIPs historically had been execution layer changes. So I put it as an EIP just thinking that's where the proposals go. And Danny Ryan had kind of suggested it. But yeah, and that's kind of the history.
Right, that's interesting. I know Danny has been supporting the EIP process, and now that we are on the verge of, like, not on the verge, actually we have made the split recently about EIP and ERC. So we hope that it will help out most of the consensus layer dev as well. Thankfully, on the call, we are also joined by Gajinder Singh, who has been added as an EIP editor, especially to support core proposals on consensus layer client team if they are willing to work on documenting any proposal. And one other thing I would like to mention, in the presentation, you had a mention of EIP-44, bound historical data in execution clients. For those who missed the talk, please check out episode 64. We have recorded a wonderful session with Alex Stokes explaining the proposal. At the moment, the proposal is in stagnant status, but it's worth watching. It's an interesting one. All right.
So just it's also
please
just an aesthetic number, I guess. EIP-44s.
Right. I think that's what they wanted to call the proposal instead of 4444. So it's just 4 4s.
Yeah.
Yeah. Well, moving ahead, let's start with the question answer session. Gajinder Singh, please go ahead with your question.
Yeah, Mark, I think it's a great presentation and it's a very clearly spec'd out idea, and it definitely makes the syncing process easy. And I can see the benefit that it allows execution clients to prune their receipts, which has not been possible since merge. And that is what one of their major pains is about. But I want to ask you, how relevant do you feel this is? Because I work on Lodestar, and we haven't implemented this EIP, and we have discussed it in house, but we are sort of waiting for 6110. So the question would be, what sort of timelines do you see for 6110 to kick in, and how relevant or how important do you think that we should go for implementation of this EIP?
Well, I'm not exactly sure what the timeline for 6110 is, but yes, when 6110 is adopted, we'll no longer need to maintain this Merkle tree. So that eliminates the need for the snapshots. I know there is an implementation, basically a test implementation of 6110 in both Lodestar and Lighthouse, I believe, that someone from the, what is that, the client, I forgot what they're called, the kind of core dev internship program was working on.
Yeah, so we, I think, are also running a small test net for 6110 as of now. But yeah, I mean, it's less about the technicality of the feature, but more about how we can basically, chunk it into the hard fork rollout process, which is already very intense and crowded, and we already have so many features comparing to go into the next hard fork. So I think the importance of this EIP basically hinges upon how desperate are the EL clients wanting to prune their data.
Sure, yeah. Essentially, yeah. And I guess how long the gap is between until EIP 6110 is implemented. So from what I've heard, yeah, word on the street is the fork after 4844 is probably Merkle trees. Now that's mostly an execution client heavy fork, and so you could maybe see 6110 getting thrown in with that just to add more stuff for the consensus devs to do. That's speculation.
Yeah, I think that could be then 1 year down the line, and maybe Lodestar should get this EIP into implementation as well.
Yeah, the nice news is like there is that Python implementation there and the test vectors, so it is like there's almost no thinking involved implementing this. So it's very quick to implement. That's why I think it has been adopted so rapidly, is just because it doesn't take a lot of work on the side of the client implementers. And like if you just basically implement the Python expec in TypeScript for Lodestar, and then as long as it passes the test vectors, it should be. So if you want to implement it, it's easy. That's the plus side.
No, I think it's just about the will to implement. Yeah, we can definitely go for it. As well as I now know that some ELs have also started sort of not syncing the entire chain. So that is also out there, and definitely it's a push for us to go in this direction as well, since the timeline for 6110 seems quite large.
Yeah, I mean, I think they had like it wasn't a difficult project for any of the devs that I worked on. Or any of the devs that I talked to. So yeah, it's just kind of a calculation like that. Is like, do you have a couple extra days that you just want to throw it in? And how useful that would be depends on how long until 6110 is, but all those are unknowns at the moment.
Right. I think it was on my question list, like how many clients have already implemented, and if there is any client who are still considering. It's glad to know that Takeo, Prism, and Lighthouse Nimbus, they have already implemented, and also Lodestar is considering to get it implemented. While 6110 is a little far ahead in future, maybe the next upgrade, it will be decided in the client developers meeting. But for people who are already interested in learning about this proposal, because it seems to be one of the significant proposal coming up in the future, you may check out episode 112 that we have recorded with Mikhail and EPF, like Ethereum Protocol Fellows, Navi Chan and Kevi Bogner. It's an interesting conversation where they have explained the changes on both execution layer and the consensus layer that people can expect with the proposal 6110. So yeah, check that out. Link will be available in the description. While 6110 is far away and all the clients have already implemented it, my question was with respect to the testing. Was it considered for any specific DevNet, or it was just as a part of like in the individual client who were taking part on testing, for example, for the Dencon upgrade? How did we go ahead about the testing of this proposal?
Yeah, so this proposal doesn't actually require any hard fork. So like it could be implemented or not implemented. And like all clients would it doesn't affect their interoperability with each other, I guess. It's just like it's a nice feature that you can add. In terms of how I went through testing, like the first thing I did was implement this in Lighthouse and just get it working. Then I had the Python implementation as well. And then in actually coming up with the test vectors, I used, I think, like Ganache at the time, and actually deployed a deposit contract, and then like I pulled the deposits like directly, and the Merkle tree branches and the roots directly from the deposit contract, just to ensure that like I was getting the data from the source and no bug in any of my implementation could have made it. So I'm very confident in the test. I have a high degree of confidence in the test vectors. And also just, I guess, due to the nature of a Merkle tree, it's like if you get one little thing wrong, like you'll definitely notice, because it's like one little bit off and it changes the entire hash. So yeah, I'm pretty confident in saying like once your implementation passes all the test vectors, and there's kind of a lot of them, like, you can, I guess, make a tree, snapshot it, finalize it, reload it, add more things, finalize them, like just do all these things and check expected results. And once I put it through as many tests as I could possibly think of, and it passed all. So that was basically how I tested it.
That is interesting to know. Yeah, we know that generally the core proposals, they are being tested on DevNets. We have DevNets for that and public testnets for that. But this is an interface level proposal. And I was generally curious, like, how do we make sure that it is also doing as expected?
Yeah.
One can just test it on prod and basically see whether you're able to add new deposits or not, right?
Yeah, I mean, that was eventually what we ended up doing. But I mean, I feel like the test vectors that I went through were so stringent because it was just like loading up a tree, getting the snapshot at every single point, verifying that it is what it should be, copying the tree to another version from the snapshot and adding the deposit, and like doing that at random intervals, and like it always came out right. So it was like, okay, seems good to me.
Yep, test vectors basically like that should allow one to basically see if there are any issues in your tree reconstruction algorithm. So yeah, they do sound amazing.
Oh, and there was also something really nice. The deposit root is actually included in the tree in the snapshot, and that was not originally there, but there is a very nice little elegant algorithm that's included in the Python specification where you can verify that the snapshot is internally consistent. So like you basically, it's just a little, oh, in fact, it's right here. So if I go here, so this nice little calculate root here, loop, which is, I mean, only as many iterations as the depth of the contract. It's a nice, compact, little elegant thing, but you can verify that the snapshot is consistent with the root. And this is one thing you can put when you've received a deposit snapshot to make sure that it's internally consistent. And so this is just
because you can match with the zero hashes and sort of build up the root.
Yep, exactly. So, and the other nice thing to note about a snapshot is that it's essentially the exact same thing as an ETH1 data, except you've added on this little list of hashes and the block height. But other than that, it's the same exact thing as the ETH1 data that basically that the consensus layer already came to consensus on.
I think this is also very nice because then you exactly know from where to start pulling your DL for the next deposits.
Yeah, that's why we added the height, because basically when you're weak subjectivity syncing, there's a good chance that your execution client is also not synced, in which case you can't get the block height until it becomes synced. And then, like, I don't know, if you include it with the block height, you just know at what block to start syncing. And some consensus clients would store by hash and some would store by block. And so just including both so you didn't have to make too many changes to your code was decided.
Interesting. Okay, I have one more question with respect to EIP documentation. It looks like it took long for the proposal to move from draft to final. I understand you mentioned about the concept of having it documented as a proposal. I'm just trying to understand here if you have faced any particular challenges or identify any limitation while drafting this proposal.
No, I wouldn't say it. Like, it's funny because I got very little feedback, so I was kind of worried that like not enough people had seen it, so I didn't really feel comfortable moving it to like review or anything. So yeah, I had left it there for a long time, but then once clients had basically already been implementing it, I was confident that like enough people have seen this that I can move it forward. So that was a big part of the reason why it just kind of hung out that way. I mean, other than that, it was kind of new. It was kind of a, what would you say, a rare experience or a novel experience being a consensus dev that was trying to propose an EIP, because like the consensus devs were kind of not familiar with the EIP team and vice versa. So that was funny.
Now we can expect more EIPs from you, Mark.
Well, I don't know. I've already got 100% hit rate on my EIPs. I don't want to risk, dropping down to 50. I gotta find something that's sure to get in.
Right. Yeah, I mean, I understand we might want to share more information about the EIP process, especially for people who are new to the ecosystem. And with the process change going on in parallel, it is really useful for people to learn about the new process. And that's why we also have this EIP editing office hour to, allow authors to join and ask questions if there are any from the EIP editors, just to make sure that they are moving their proposal as needed. All right, we are coming close to concluding today's talk. Do you have any message to share anything specific to shill about the client or any alpha that you would like to share with our listeners?
Well, I've been doing a lot of work on PBS, and that seems to be kind of in the weeds. In fact, Mike Neuter called it the infinite buffet because there's so many options to pick from. And after looking at all of them, I've come to the conclusion that what we should do next, the optimistic roadmap, where we start modifying the MEV boost, the builder specs, so that we're moving slowly towards enshrinement, but we're leaving it with the builder specs, and we kind of see how the community likes that. That's how we move forward to test the waters, because that's the next thing. So that's my message to the Ethereum community. Let's move forward with the optimistic roadmap for PBS. Very niche message.
Thank you so much for that. I know there are a lot of research work going on in parallel. You just mentioned about PBS, and I'm really happy to share that we did record a very in-depth discussion with Barnaby Mannath, who is a researcher and has been working on PBS. So people who would like to learn more about this initiative as well may go ahead and check out our episode number 93 on PEEPanEIP playlist. I think we are trying to come up with all these research work going on in parallel. So community may have their voice about what they would like to see next, and that may help us decide our next upgrade proposals here. I think this was really interesting discussion, short proposal, but interesting. And I learned a lot about something new that is coming up here, and there are parallel work going on. Mark, we thank you for joining us on PEEPanEIP and talking about EIP4881 deposit contract snapshot interface, which is in final status and is available as an interface standard. On this note, thanks to our YouTube viewers for watching and podcast subscriber for listening to the special episode on interface EIPs. Should you have any question on this or any other topic, let us know at eCatheaders Discord. Check out the description for more info. We'll be back with another interesting talk. Until next time, keep watching, keep listening, and keep sharing your love with Ethereum Catheaders. Cheers.